I'm in the mood for some programming, but it's pretty late, so I'll only do something small, like contravariant lambda parameters. I actually think explaining that will take longer than implementing that, but I'll try my best. So in many languages, you have a concept of subtypes. For example, in Java, you can define a class animal, and then a class cat that extends animal. And then cat is a subclass of animal. And what variance describes is how parameterized types or generic types or container types, how they relate to each other. So let's say you have a list of cats and a list of animals. Oh, well, yeah, that's usually written with like brackets like this. Sure. So the question is, how do they relate to each other? You know, if we cat is a subtype of animal, how do list of cat and list of animal relate to each other? If these types are covariant, then they are also a subtype. So if cat is a subtype of animal, then list of cat is also a subtype of list of animal. And that's useful in situations where, for example, let's say you have a function that accepts a list of animals, and that function iterates over the list. It maybe prints the animals. If that list accepts a list of animals, but you only have a list of cats, you can also pass that list of cats to that function, because it can still iterate over that list and get the individual cats out of there. And because every cat is an animal, it can also get, you know, whatever properties an animal has. It can treat that cat like an animal. There's also the contravariant relationship, which is that this is kind of the reverse of the inner types. So if cat is a subtype of animal, then list of cat is actually a supertype of list of animal. And this might seem strange, but consider a function that appends something to a list. For example, a function append kitty or something that creates a particular cat instance and then appends that to a list. That function maybe accepts a list of cat, but if you have a list of animals, or even like a list of objects or something, like something more generic, you should still be able to pass that to the function so that it can then append the kitty to that. You can also append that to a list of animals or to a list of objects. Yeah, but you cannot pass a list of animals to a list. You cannot pass a list of cats to a list of animals if that function tries to append something there. For example, if it tries to append a dog somewhere, the function might accept a list of animals, but you're not allowed to pass the more specific type list of cat, because the function can't append a dog to a list of cats. Yeah, and then there are other cases where list of cat and list of animal, like, they just don't relate to each other at all. They are neither a subtype nor a supertype of each other, and that's called invariance. Yeah, so as you might have noticed, whether something should be covariant or contravariant or invariant really depends on how you use those data structures. If you only read from data structures, like iterating over a list or getting some properties from an object, then that usually is a covariant relationship. Whereas if you put something into a data structure, you want a contravariant relationship. And if you read and write to a data structure, then that should be invariant. In my programming language, Plum, data structures are mostly invariant, except for enums. So let's actually show that. Yeah, I have here, for example, a switch on some bool. And this one branch evaluates to an enum of false, and that other to an enum of true. The type of this is actually just this. It's an enum type with a single variant named false. And this is a type with a single enum variant named true. And these types, they get joined using, you know, kind of an implicit cast here. We join these types of false and true to an enum that is false or true, true or false, that's equivalent. So enums can be joined. And this works even if you have, some branch that evaluates to A or B and the other evaluates to B or C, then those get joined to A or B or C. And because data structures in Plum are immutable, you can only read from data structures. That's why this kind of covariant relationship for enums makes a lot of sense. However, there's one case where it doesn't, and that is lambdas. So lambdas are created using this backtick, and lambdas, they accept parameters. So for example, if you have, let's actually go here. If you have some lambda that accepts some value, and that is supposed to be an enum, A or B, and it produces an int, and you actually have something and you switch on that. And in the first case, you evaluate to something of this type. A lambda that takes an A or B and produces an int. And you have a second branch that evaluates to another lambda of some other type, like B or C. And yeah, let's for fun say that this evaluates to A or B or C, and this to B or C or D. Then what should be the type of this entire switch statement? Like if you assign that to a variable, what should be the type of this variable? Again, this lambda here can work with A or B or C. This lambda can work with B or C or D. I think the type of this here should be some lambda that can work with B or C and return an int. So lambda parameters, they behave different than the lambda return values. The return values, if this here returns x or y, and this returns, I don't know, y or z, then this entire thing returns x or y or z. So if you don't know which of these lambdas was chosen, so the return type of these, they get kind of joined, they get unioned into x or y or z. You need to handle each of these cases. Each of these can occur. But the parameters, they should not be unioned. No, they should be, you want the intersection of these enums. And that's what I want to work on today. So contravariant lambda parameters. Using the relationship of contravariance, where if something is a subtype of something else, like B and C is a subtype of A, B, and C, use that for lambda parameters. All right, now to actually implementing that. So I think in the compiler, in the type system, I actually have a function for unioning types. Yeah, some boilerplate. And the interesting part is down here in lambdas, I have this big to-do that explains exactly this. So if I have some lambda that by now enum variants are lowercase, that was not the case before. If I have some lambda that returns that accepts an A or B or C, and it returns x or y, and another lambda that accepts a B or C or D, and it returns y or z, then those types should be joined to a lambda that accepts any B or C, the intersection of these types, and it produces x or y or z, the union of these types. The union of the return type, that is already done. Like we just call this function, this union function here, recursively. We call ourselves recursively. But the intersection of the parameters, we don't do that yet. And that's what I want to do today. So basically, just look at, well, have some sort of intersection function, I guess. I'm just going to copy this, I guess, and we'll go from there. All right. So intersection logic that accepts two types and is supposed to print the intersection. If one of these types can never occur, then an entire thing can never occur. If the first one is a type variable, then the second one has to be that type variable, has to be that same type variable. All these types are not compatible. Yeah, if these are primitive types, well, they have to be the same primitive, sure. Yeah, I do have arrays, and yeah, I don't want to go into that yet. All right, here I have structs, so we just take the individual fields and we intersect them. Like that, I guess. Or intersection. Yeah, we'll see how that works out. Yeah, and for enums, this is the interesting case. Here we have the variance of A, we have the variance of B, and then we build up these kind of final variants of the intersection type. And what we did for unioning is we went over the variance of A and put them in there, and then we went over the variance of B and put them in there. And if both A and B are in there, so if the variance, if this variant is already in this variance string inside there, then we would also union these. In our case, we only want variants that are contained in both A and B. So we kind of do, for every variant in A, variance, we say the argument of the variant is the value. But first, we also want to make sure that that same variant is in, the name, I guess, is variant.key. We have the value, and then in B, the B variance, that same name should be in there. If it isn't, then we'll just return none. Like these types are not compatible with each other. Hang on, no, then we'll just continue on to the next variant. And then we'll also need to make sure that the overall argument, that is the intersection of the A arg and the B arg, and currently unioning, well, we'll get to that. All right. Yeah. So then we'll only have the variants that are contained in both A and B, and their kind of argument, the payload of those variants that is intersected. This lambda stuff is still a big to do, but then in the union, unioning, we can actually be smarter about these arguments, because they don't have to be exactly the same. Even these lambdas, they are compatible. They just need to be intersectable. So what we do is, I guess we'll just build arguments, which will be a list of plum types, and then for every, well, both in, zipping A lambda that args dot iter and B lambda args iter, we try to intersect these. We get the intersection of the A and the B. If that doesn't work, then sure, we'll return that doesn't work. And to resolve that, we're going to push that to the arguments just like that. Yeah. And in the end, we'll just have a slice of arguments, which we can just use down here. All right. So when unioning, I think it makes sense to have sort of a note, like a comment in here. Yeah. Lambda parameters are contravariant. The return type is covariant. Yeah, and then this is the kind of logic there. Changed quite a lot. Like the switch syntax, the lambda syntax, enum syntax. All right. So similar to how we did that for unioning, we just have this unioning logic, and to guard against recursive types unioning themselves, kind of, and we also have this right here, which just checks that we are not currently unioning these. If we are, then we'll just say, well, these, that works. They're recursive. Yeah. And I think I'll do something similar for intersections. So getting the intersection of two types, and yeah, currently unioning. Gonna work on that. Yeah, but it just calls the intersection logic. Yeah, that's basically it. And yeah, in here, if we encounter a lambda, and oh damn, here it goes. So if this right here is a lambda, so this is a function, and hang on, this is an expression that evaluates two different lambdas, and each of these lambdas, again, like this is A is of the type a lambda that accepts A or B, and returns, I don't know, an int, and this right here is a lambda that accepts B or C, sure. Then that entire thing should be a lambda that then takes a lambda of A or B or C. So these, I think, should be unioned again. I'm not entirely sure about that. Let's just see how that goes. So, assuming the condition is true, then in here we have some sort of lambda. All right. Oh yeah, and we can pass, if we have a lambda that works with A or B or C, we can then pass that into this lambda, which accepts something that can only work with A or B. But our thing that works with A or B or C is still compatible with that one. Whereas if we are in this other case, then our lambda that works with A or B or C is also compatible with this one. Okay, so the arguments, if they are lambdas themselves, they are unioned again. The union calls intersection, and the intersection calls union for lambda parameters, because they are contravariant. They kind of flip around for each level of indirection. All right, yeah. Yeah, the return types, they intersect. But the arguments, they get unioned. Similar to how they get intersected in, well, up here. Let me see, that is, yeah, this right here. I do wonder whether whether it makes sense to join these. You know, to join unioning and intersection, because they are pretty similar actually. And also this currently unioning, we want to allow a lambda that does some unioning and then suddenly it flips to joining lambda parameters. And then maybe in there it switches to unioning again. Like, if that is recursive, we want to allow recursive types across that kind of boundary between unioning and intersection. So we actually need to unify these. I think the way to do that is by actually merging these two functions, yeah. Instead of union, maybe have some sort of, you know, join two types using, I don't know, some join mode maybe. Oh, that is horrible. And that is either union or intersection, something like that. And then there is flip on join mode that returns another join mode that is, well, yeah, it switches on the mode. If it's union, then it's join mode dot intersection. And if it's intersection, then it's join mode dot union. Something like that. Yeah, and currently joining is actually currently unioning. Let's rename that to currently joining. And that actually contains a 3 tuple. And yeah, maybe let's put the node at the beginning, because that is quite important. Alright. And this is a 3 tuple of the join mode and the plum type, basically the arguments of this function. And this is the join logic, which is down here, which works it's kind of generic over mode. You can think of that as being generic. Yeah, this is different depending on the mode. So if we are if you're unioning these, then that's B. If we are getting the intersection, then there's A. And similarly here. Alright, this stays the same. This is the same among both. Same with this one. Same with that, yeah. Same with these. Except we are not calling union, we're calling join, using our current mode and currently joining. And yeah, we put that over there, put these in here. Oh. Yeah. Yeah, the logic for enums is actually different. That's the big thing. So if we are unioning, then we are doing something. If we are calculating the intersection, then we are doing whatever we do down here. yeah, for lambdas. Yeah, for the arguments, we are kind of joining them, but with a flip mode, so mode.flip. Because this is contravariant. Yeah, and the return type, that is joined covariantly. Alright. Yeah, and then we don't need this one right here. That is just kind of merged into this one. Yeah. Alright, I like that. One thing, this find, I think, requires equality to be implemented. So let's actually have an equals function for join modes that just checks if, well, if A is union, then it checks if B is union, and if it's intersection, then it checks if B is intersection. Yeah, like that. Alright, and unioning two types is actually just joining them with join mode union and an empty list of 3 tuples of join modes. And the unioning a bunch of types just unions the individual types. That makes sense. Alright. Alright. Yeah, this needs the mode, sure. What's going on down here? Yeah, this is currently joining, and this needs the mode, and kind of join these. I mean, yeah, the mode is unioning, so. Still. Yeah, same here. Right, let's see if that compiles. So 821, down here we need these get joined with the same mode, just like that. Clean, very clean. Okay, compiles. Now the interesting part is going to be creating an example for this and testing this. So let's say that we have, I don't know, we check if A is equal to 2. If it is, then we will just have this enum that takes some value of the type, an enum that is A or B. Yeah. Yeah, like that. And it returns 5. And in the case of false, we have a lambda that accepts that. And this shouldn't compile, because the return type is not a string. But the error message is going to tell us what kind of type the compiler inferred here. And that's going to tell us if that worked. Ah, yeah, the good old compiling the compiler, taking a lot of time. Okay. Yeah, we need an equals function in scope. So let's import that equals for int. Yeah. None.unwrap. Now that is interesting. Oh, I see. Compile cast fun body. Yeah. fun in casts. Okay, so when we are compiling a cast function, which is, we figure out where do types not perfectly align, but they are assignable to each other. There, like that is where we need to insert a call to some sort of cast function. And for lambdas, what we do is we kind of create a new lambda that wraps the original lambda. So we know the type that we want to convert from. We know the type that we want to convert to. So then we'll create a closure, aka kind of a struct containing the captured variables. And in our case, that's not really a struct, that's just the original closure that we are wrapping right now. And then inside the body of that new lambda that we're going to create, we have some parameters. Yeah, the original parameters of the lambda type that we want to compile to. We have this kind of inner closure. We get that, and then we have that's the from lambda that we want to call. Yeah, and then here we just call that. Right, before we do that, and just passing our parameters to, to a slice, we want to actually cast those. So kind of map these, meaning we create a list of the cast parameters, and then for every parameter in the parameters, we just, I'm not entirely sure, we cast that, which means push cast, I guess. Something like that. Yeah, lambda body.push cast with a from value, which is just going to be the parameter, which is an ID. And then, oh, hang on, the from value. Yeah. Then the type of that, I'm not entirely sure about that. That is the from lambda type. Let's see. Let's kind of iterate over that and enumerate these, and then this is the actual parameter item from there. And the from value type is the from lambda type dot args get at that index. That's going to give us the type of the parameter in the from lambda. Yeah, and we're going to convert that to the lambda type from the to lambda. And the context, I don't even know what that is, to be honest, but it's probably important. Okay, and then that cast parameter is going to be pushed to these parameters, these cast parameters, and then in here we'll actually call that original from lambda with the cast parameters. Oh, hang on, this may be wrong actually, because in this case we want to push a cast from the to lambda type to the from lambda type, kind of the other way around, because these are contravariant. Let's see if that works. I mean, the compiler compiles at least. Okay, compile cast fun body, and then in here we have some sort of unwrap. Oh, hang on, compile cast fun body. Compile cast fun body. Where's unwrap in here? For struct types, we make sure that the from type is also a struct. Makes sense. For enum types, same thing. Oh. Interesting. Maybe let's print the cast. compiling, and then the signature, which is just going to be cast from something to something. Then we'll see the cast and those types that we try to cast between. Yeah, I was wrong in the beginning. Implementing this does take a lot of time, just because of the usual debugging stuff. Oh, no, this is not okay. Oh, I see. So we do something here. Hang on, we have some function that accepts an A or B, and another function that accepts a B or C. Apparently, at the end of this switch branch body, this function is cast. The A or B to int function is cast into a function that only works with B. That's apparently the type of the entire lambda. And the same thing happens for this function right here. Yeah, that makes sense. But then in the end, we try to cast these. That's interesting. Like, I know that this does cast to one another, and like it tries to, but I think that should be caught earlier in the compiler. What happens when we are compiling a function? Hang on. Can we maybe print the... Oh, I see, the egg is kind of the type check version of our program. So let's look at the something to egg, toast to egg compiler stage. Mod, sure. So we are compiling the individual functions, which probably goes into this compile fun kind of thing. And here we have parameter types, the returned thing, and then we just push cast. I think what we need to do here is we need to check if the types match, basically. This toast function, it claims that it returns something. Fun dot, what is it, return type. But compile that, please. And then we need to make sure that that our return type is compatible with that one. I think there is actually like an is assignable to or something. Yeah, that just unions those two types and sees that that's still the same type as we are compiling to, is assignable to. So we check that this type that the function body actually returns, that is assignable to what the function claims it returns. Or if that's not the case, then we just return an error. And this error has a message. Function claims that it returns the source of that is, I don't know, the function name. Is that fun.name maybe? What source? Does that exist? I have no idea. Alright, let's see. This will probably not compile because there are some weird things. Yeah, compiling a toast type. Yeah, that needs a map of Plum type defs. I think we have that. We have this types thing. Oh, look at that. Map to Plum type defs. Compile this using the types. Why was that not caught before? That is... Oh, hang on. Bool does actually exist. Oh, shit. So something is going wrong here, apparently. This was just supposed to be a short video. I'll try to use bool, but that type doesn't exist. What? Not sure about that. Really not sure about that. What do we do with these types here? We just do parallel type.compile with a module types. That might be interesting. Oh, hang on. Oh. This is already the return type. I see. Yeah, that is already what we have here. We just need to check that returned.type probably is assignable to the function return type. That makes sense. Yeah, returned.type is not a thing because, of course, returned type is fun dot. We do have a DAG in here, don't we? Yeah. DAG.get ID, get returned. I mean, this is shorter than typing out returned type, so. Well, DAG type off. I think that's the thing. All right, that seems to compile. That's a good sign, and hopefully we'll get an error that the return function returns something different. We do get that error for a different function. That is still a win, I would say, because now we're catching errors that we hadn't. There were errors in the standard library apparently, but now we're alerted of them. All right. So toList of an iterator calls next on the iterator. If that is empty, then we just return empty. Oh no, this works for linked lists, but not for lists. Yeah, no. Nope. Let's try toList on an iterator, really. I think we'll just do iterator.fold, I think, with an initial state being an empty. You know what, let's not do this for now. Let's just comment it out and leave that for later. Not the main topic of this video. So, okay, so last of an iterator. Turns maybe A. Alright, but this one right here returns a previous. This returns an A. If it's empty, then it just returns previous. Oh yeah, this returns an iterator actually, I think. That's not good. Should be like that. Okay, this claims that it returns this. And iterator, like a function that returns this, empty or more of this thing, with the rest being 3 levels up. 1, 2, 3, right here. This rest is another closure, another lambda, that makes sense. And then the item is an item of the type A, index is int. Alright, makes sense. But it actually returns this one. Empty or more, with the rest being empty or more with rest and index. Yeah. And this rest then is another iterator that is either empty or more containing a rest. And an item that is an item at an index. It does seem correct. Just like a more, you know, like convoluted way of writing this one. Yeah, not sure what to do about that though. That should be the same type, I think. Let's say function has returns something different than its claimed return type. Yeah, and then have the claimed type in here. Then the actual type. Yeah. That's cool. Just make that kind of line up and yeah. Well, seems like some of the type stuff is not working out super well. Let's go through this one and just check that we call the correct join thing here. So currently joining, we try to find that tuple with the current mode. If that exists, then this is just a recursive type. Yeah, and then we extend these types one level. Alright. Then we call it join logic. That actually, like there is no never type in these type variables, they have to be the exact same. Primitives, well, yeah, they have to be the exact same as well. The never is unreachable. Struct is just joining the individual field types. Yeah. All right. And then enum is, well, switching on the mode. If we are trying to union some enums, then we put all the variants into this map. If we're calculating the intersection, then we are only putting variants that are contained in both enums into the map. That makes sense, yeah, that does make sense. For lambdas, we do some stuff. We check that all the arguments, we join them with a flip mode, intersecting them if we are unioning them if we are intersecting them. All right, and then turn that into a slice. Sure. The return time, we get that. I'll put some new lines in here to make that a bit more friendly. Yeah, and the return type is drawn with our own mode. All right, yeah, that seems correct to me. But apparently that does not work for some reason. I really don't get it. These should be the same type. I don't know. I'm not sure about that one. Like, we are joining these and then we check them for kind of approximate equality, which is up here, checking if these types are equivalent. You know, let's kind of log that maybe. Is from assignable to 2 unioned, and then just print that one. Sure. Okay, I think that already fails in the unioning here. Interesting. Let's maybe print whenever we are unioning something. Maybe that makes things a bit easier. Like the joining, let's see, from join mode, yeah. Here let's just do joining A and B. Last thing is joining int at int. For primitive types, we check that B is a primitive type, yeah. We check that names match, yeah, and that the arguments are exactly the same. Yeah, that does seem reasonable. Debugging is kind of horrible. Well, that's a long ass feedback loop. Okay, joining some types, int at int. Oh no, an error occurred. Why? I mean, when we return false, oh, you know what, and here, Hmm. A union failed, and then there was nothing in there. Well. Oh, I see. So add an early return here. Oh, it's gonna be a lot of fun cleaning that debug thing up later on. But we should kind of see a stack trace of what we tried to union. Okay, so we tried to union this type and this type. Oh, you know what, let's print that a bit better. Let's do... that. Right, we try to union these two types. Yeah, that seems reasonable. So in order to do that, we kind of extend these types at the bottom, which means the first type is going to be that. The second type, well, for the rest, we're going to insert that into there. Indeed, they are different. Hang on. For some reason, they are different. We have this ampersand with we do have this enum with empty or more. Looking at the parentheses, this is the more type. Oh yeah, this only has rest and index. Oh, well, yes. Yes. This is supposed to be an item that then contains the index being the start index and the actual item being a model item. Type errors. Like this is... Oh, look at that. The actual thing I wanted to see. Yeah, the main function claims that it returns a string, which is just a struct containing UTF-8 bytes, which is an array of bytes. But actually, it returns this, a lambda that accepts a b. And we can have ABC and BCD in here, and they get joined to an enum that is B or C. Wow, that is exactly what I wanted. It turns out the error reporting is just like the type reporting. Working with types is horrible because they expand to these kind of monstrosities, and yeah, that's really, really unwieldy. Huh. I'm not sure what to do about that. Let's maybe I do want to keep some of the error handling here, actually. So how about this returns not a maybe, but a result with a string that explains why those types don't match. And then here we have a stack. We try to join them. If there is some type, then we just return OK with plum type and string. If it's none, then we return error. Plum type string. And then this is going to be wrapped, and we will create a string builder. And then just print to that string builder instead. Alright. Yeah, and then we don't need this kind of logging here. But we do have a nice stack traces. That's exactly what I want. All right. If that doesn't work, with an error, then we just return an error. Oh, hang on. I think we can even do that. Let's see. Yes, perfect. All right. Yeah. I guess contravariant lambda parameters work. And with that, I'm gonna stop for today. Yeah, I guess see you in the next video. Bye.